Hello, my name is Jana Bektas. I'm a research assistant at the Communication Networks Institute of the Technical University of Dortmund in Germany. I will now present you our work entitled On the Benefits of Demand-Based Planning and Configuration of Private 5G Networks in the course of the IEEE VNC 2021 conference. My presentation is structured as follows. First, I will clarify the question why private 5G networks are important and why, in this context, automated network planning and configuration is necessary. Then I will present our proposed method for automated network configuration based on an experiment showcase. I will then go on to an evaluation of the proposed system and finish with a conclusion and an outlook on future work. So why is the topic of private 5G networks so important? In various countries all around the world, it is now possible to use 5G spectrum in the context of private use. The spectrum usage licenses of these so-called private 5G networks are usually awarded to companies after an application is submitted to the relevant authorities. We observe that especially in Germany, there are already more than 150 local frequency assignments, and we expect this trend to go on in other countries too. The next question is, why do we need private 5G networks? Private 5G networks are seen as key enablers for customized communication solutions. For example, guaranteed quality of service is enabled because the assigned frequency spectrum resources are granted exclusively, in contrast to technologies like Wi-Fi in the 2.4 GHz band, where interferences are common. Additionally, fully digitized environments can be deployed safely for industrial applications and critical infrastructures. Also, ad hoc and temporary deployments are made possible, where QoS requirements in the context of fast deployment and rapidly changing local conditions can't be met with traditional static mobile communication networks. This also means that in order to maintain QoS and keep interferences low, extensive network planning is required. Traditionally, coverage and capacity planning were sufficient to fulfill the basic QoS needed for public mobile communication networks. In 5G, especially in private networks, new technologies such as QoS flows, TDD patterns, as well as network slicing are introduced to meet the complex needs of today's applications. This means that in order to configure these complex features, automation could be utilized. I will now present our proposed method for automated network configuration based on an experiment showcase. Our proposed method for automated network planning, which is demand-based and possibly machine learning assisted, works as follows. First, the machine learning creates a network model and configuration for the coverage, capacity, as well as a configuration of the network. The configuration is then forwarded to the network configuration and control module, which implements the different interfaces to the network infrastructure to configure parameters like resource allocation or uplink-downlink time division duplex patterns. The TDD patterns are the main focus of the work and experiment showcase presented here. The configuration is then sent to the elements of the network infrastructure and applied correspondingly. Normally, the process would end here, but we propose a key performance indicator or KPI monitoring and a network evaluation module where KPIs are analyzed passively or actively in form of stress tests to validate the configured settings. If unstable operation or anomalies are detected, the machine learning model is triggered again to optimize the configuration and the cycle starts anew. This means that the configuration is adapted constantly to meet changes in the network conditions or application requirements. Note that the implementation of such systems is open and a matter of future work, but the work here shall demonstrate the need for these methods. In order to demonstrate the need for such systems, we created a video of our experiment showcase called Racing with 5G Speeds, Reliable Ad Hoc 5G Campus Networks, which can be watched following the link or scanning the QR code. In the experiment showcase, we present a downscaled Formula One racing event with real 5G uplink video streaming. There, two 5G-powered self-driving miniature cars based on the F110 platform are placed on a miniature racing track in order to emulate a racing scenario. The race cars send uplink video streams of their first-person view using the private 5G infrastructure at 3.7 GHz private 5G network frequency band to a video decoder. Similarly, a 5G-powered aerial drone cam is streamed to the same video decoder over the 5G network. Note that, in contrast to traditional applications and mobile communication networks, the application of video streaming is strongly focused on uplink. The technical architecture of the experiment showcase is shown on this slide. We utilize Quectel RM500Q on the F110 platforms as well as on the UAV. For base stations, we utilize the Amarisoft Callbox Classic on the 3.7 GHz private 5G band with 5G standalone new radio air interface. The experiment showcase considers two system states. The first system state represents a typical public network operation where the TDD pattern is heavily downlink focused. In the case of the application of uplink streaming here, the downlink is oversized and has a lot of unused capacity, whereas capacity is missing in the uplink video stream. This anomaly is detected and thus the configuration is adapted to system state 2, where we utilize the demand-driven racing event configuration where the TDD pattern is heavily uplink focused. This means that the resource demand and capability are now matched and the configuration is optimal. Note that in this showcase we manually switch the configuration, whereas in our vision and in future work the mismatch is detected automatically and the right TDD pattern is selected and applied. We will see more on that on our simulative evaluations. Now I want to show some results taken from our experiment showcase as well as some validations using simulation results. The first clip shows system state 1 where the typical public network operation is utilized. As you can see, the first-person view of the racing cars is transmitted without problems and smoothly, whereas the full HD stream of the UAV called Drone Cam experiences massive interruptions and artifacts. The video shall demonstrate the quality of experience, which is not that visible looking at raw measurement data. This is important because even if the data rate on paper is often sufficient, the video may be poorly received by the viewer since the devices in the uplink cannot transmit so often that the video continues to run smoothly. In the second clip, the demand-driven and uplink-focused TDD pattern is utilized. Here you can see that the videos run smoothly because the uplink data rate and sending occasions are massively increased. We also conducted some simulative validations based on the Omnet Simu5G simulator, where we tried to replicate the conditions in the showcase experiment as well as possible. The details of the simulation configurations are shown here. Here we see the packet delivery ratio on the left side and the latency on the right side over the number of TDD uplink slots respectively. As you can see, the downlink-driven configuration shows a PDR of roughly 80% and a latency over 100 milliseconds, whereas the uplink-driven configuration has a PDR of 100% and a latency of roughly 20 milliseconds. This is consistent with the observations in the showcase experiment, where all video streams ran error-free only after a certain number of uplink slots were used. Plots like these based on simulations can be used in the future by the machine learning model to estimate the PDR and latency and thus influence the quality of experience based on simulation results. I will now conclude the presentation with a summary and an outlook on future work. In this work, we developed a small-scale 5G new radio-based experiment platform for dynamic racing events. We also showcased the need for demand-oriented configuration and planning of private 5G networks based on a real-world downscaled Formula 1 scenario. Also, we developed a vision for future ML-assisted network planning and adaptation parallelly working with the live network operation. For future work, we envision a system in which a digital twin of the network and its participants is constantly utilized in conjunction with the real network operation. This not only includes the network operation center, but also for this example, the racing team control and the entertainment services. This means that during network planning, we can constantly observe the application as realistically as possible and can thus guarantee a good quality of experience, which can then be realized in the real-world scenario. This concludes my presentation, so thank you very much for your attention. For further questions, you can contact me via email, and for more information on the chair's other scientific activities, you can check out our website or our YouTube channel. Goodbye.